I think I will turn off the chat today. I mean, I will hide it from the screen. I'm not sure about it. Some people suggested it in YouTube chat. I mean, in YouTube comments. Maybe I will turn it back at the end or between problems. Hi, Twilly. Software and game dev? That's just programming. Hi, Kingpin. Live on YouTube? Yes, it is live on YouTube. Here. If you have done homework, the stream will be more beneficial for you. So it's up to you. It's not high school where I will check if you did the homework or not. Let's start. I'm turning off the chat for now from displaying it. Maybe between problems I will turn it back on. A few days ago I did a lecture on various square root techniques. We talked about 6 techniques and few problems. There were harder homework problems, and we will discuss those today. Those 4. 2 of them are just statements here, and 2 of them are links to something in code forces. First one, P6. We need to do knapsack, but in better time complexity. Given set of numbers, check if there is a subset with sum equal to x with better than quadratic time complexity. We need to get off the target sum multiplied by square root. And we'll use one of the techniques here. Well, one thing is that I already mentioned knapsack last lecture, but let's see what makes sense. Split the sequence into blocks of fixed size. That doesn't help too much because we don't have queries about ranges. Objects into light and heavy. I said that it's common for vertices, but actually it's about frequency. So this is the method. Then time of queries, there are no queries. Most algorithm, again, no queries. Sum of lengths is s. This is related. So maybe we're doing something related to technique 2. Also, technique 5 is very similar. Yeah, I think 5 is the closest. We will here consider numbers with small and big frequency, actually with the same code. Link doesn't work. Here we go. We're solving P6. And maybe it's a good idea to put info here. P6. Here. There will be problem number. There is some command cooldown. So if somebody used link, then you will not be able to. How can we think about this problem? Well, I'll start with the brute force, not really brute force, but dynamic programming in this time complexity, or just x squared, n times x. That's the brute force, right? Yeah, we have dp of size x plus 1. We start by saying dp of 0 is true, and then for every element in sequence A, for every x in sequence A, we say if dp of I is true, then dp of I plus x is true. And we need here iteration backwards with I from uppercase x down to 0. I shouldn't say here. Maybe I will call it like element. If this is true, then mark this as true as well. Now, there are some repetitions maybe in this array, and square root of s appeared in one of the techniques, exactly in this one. If the sum of numbers is s, then there are at most square root of s distinct numbers. We can, given this array of numbers from a1, a2, and so on up to an, we can group them and find frequency of each of them. For example, if a is, I don't know, 3, 5, 5, 1, 5, and 3, I can just remember that 3 times there is number 5, 2 times there is number 3, and once there is number 1. But can I do something like this, just going once through the array? It would be very nice, because then problem is solved. The claim is, from technique 5, that there are at most square root of s distinct entries here. Like here there are 3 distinct entries, 1, 3, 5. What can I do? In a knapsack, can we handle the fact that some object appears up to 3 times? Can I simulate this? It turns out that yes, it's possible, and there are 2 ways to do it. One way is to do it with actually not bool but int dp, where at least temporarily I will count the number of ways to get something. And here, this transition for every I, or the sum so far, I will call it s. For every s, I already know that I need to transition like this. And for the number of ways to achieve something, I can do this, dp of s plus l plus equal dp of s. If I go backwards here, then this counts the number of ways to get the every sum. But if I go forward, so if s goes from 0 up to x, then this will allow taking the same element many, many times. This is a knapsack where we can take the same element many times. And now I don't want to say infinitely many times. I want to subtract something. Like in, when you want to use prefix sums to only add something to a range, you can subtract something later on and it will cancel the thing. For example, if you do dp of 5 plus plus, but then dp of 8 minus minus, and then you run prefix sums on this, this will add +1 on the range from 5 to 7. So similarly, here I'm going to say dp of s plus l times frequency minus equal dp of s. This is the moment when I want to stop adding this thing. So dp of s plus element will get this value. Then this thing will propagate to the next value, and so on. But eventually we will stop here, I hope. Is that okay? Now, I'm not that certain. Let's analyze some example to see what I want to do. I haven't implemented it. If there is one way to get sum 0, and now let's talk about element equal to 2, and it appears 3 times. Then I want to put this one here, here, and there. Let's create some more elements. So I say +1 here. This thing gets updated to 1, but also -1 here. because I know that this one will keep propagating. I want to cancel it eventually. Now this one will update 2 elements later by +1, which is nice, but the bad thing is that it will also update this guy to -1. I don't want this. This shouldn't change. Then this +1, it will update this +1. That's good, but also it will update something on the right by -1. Then this thing will update 2 elements later by +1. That's 0. Great. But now I didn't want this. So moving far away should be done only using white elements, those not affected before, I think. So +1? No, the +1 would completely mess up I only want to jump by multiples of L. I think +1 should be in brackets indeed. Like this. Wouldn't the numbers in DP become huge? Yes, that's an issue that we will resolve. So to do handle huge values. Okay, so I believe that we should here always do this, but only subtract using the previous row. So always say dp is equal to copy of old dp. I mean, old dp is equal to dp. dp is also equal to old dp. Then do this and we should be fine. I assume that dp and old dp are vectors. So we add using previous value. This will keep getting propagated, but eventually it will stop. Yeah, looks good. Hash map? No, there is no need for a hash map. This is just an array. Don't use hash maps unless you have huge indices. Okay, now regarding huge values, what I want to do is just after running this, which I hope is now okay, you can here at the position of exclamation mark just minimize everything with 1. So for every s, say dp of s is minimum of dp of s, comma 1. Now, because I don't want to store huge values, I think it can be proved that here temporarily we will not get elements bigger than n or so, maybe n squared, so it's fine. Because let's remember that at the end I don't want to know the number of ways. I just want to know if it's possible or not. Write the frequency in base 2 with the log2 and trig. Oh yeah, we can do that. We can do that indeed, but you will, the time complexity will be multiplied by logarithm. What you're suggesting, Smile, will give us n squared of n times log. If we do knapsack with the standard logarithmic trig to handle some frequency. Now I'm not that certain about this. I'm scared. Prefix sums and these forward sums are equivalent, really. There is no difference. Okay, so this is one solution. I hope that I'm not messing things up here. And now there's solution number 2. Also, we improved this to x multiplied by distinct, where we know that the number of distinct elements doesn't exceed square root of s. So this is already a good solution. Second possibility for handling these elements with some limit is that I will temporarily define not boolean but a pair boolean comma int dp of x plus 1. Actually, I think int enough is okay, but this int will be the minimum number of times I need to use this element. The min number of times to use this element, this new element I'm looking at. And now this part, so considering using a new element, will just be for every s, if dp of s dot first is true, dp of s plus element, right? Yeah, plus element is what, minimum of itself, comma a pair true, comma what, the number of times we need to use it, as second plus 1. Actually, this true is not necessary at all. Ignore the true, basically. Just let's focus on the second element of a pair, this thing. And also after doing this, for every s, if dp of s second exceeds the limit, then dp of s is false minus 1 or something like that, because that's invalid. Yeah, so it's a linear dp, just like here, this one, but without counting the number of ways to achieve something. Just for every sum, I want to know, can I get this sum? And if so, how many times do I need to use the element I'm looking at? For example, if this is at position 0, I have true, everything else is false for now. I cannot achieve anything else, any other sum. And now I consider element ai equal to 2. Then this value will be set to 1, this value will be set to 2, this value will be set to 3, and this means how many times I need to use the element I'm looking at in order to get this sum. And then if you look at frequency at the end, frequency equal to maybe 2, 2 times I have number 2, then I know that this is not a valid state. So I need to change this and say false. And that's the solution. Again, we have the time complexity of x multiplied by the number of distinct elements, which is x times square root of s, just like the problem statement requires. P6 done. It boiled down to handling an element with some frequency, and that there are methods for that. Also the logarithmic method, but that's slower. We move to P7. What do we have in P7? Nope. We have jumping forward. Jumping forward. For every position, we know how far to the right we will jump from there. And now, starting from some position, we need to know how many jumps we can make and where we will finish. Then there are also queries that some edge changes. Given a position, we are given new position to which we jump from here. That's the problem statement. What can we do about it? Let's look at our sequence of techniques. Squared decomposition, split the sequence into blocks of fixed size. This will be the solution. Splitting objects into light and heavy. Here we don't have frequencies or degrees, so it doesn't make sense. By the time of queries and rebuilding the structure. This I think makes sense. We can also try third technique. I don't know, maybe it will work. Most algorithm, nope, because we don't deal with ranges. And sum of lengths, again, no frequencies or lengths. And here this is just randomized problems. So 1 or 3, I think, makes sense. Heavy vertex, light vertex, or rebuild. But what is heavy and light vertex? I don't think technique 2 makes any sense here. For a moment, maybe I should have turned down the chat a few minutes ago. Jero, yes, I think that logarithm trick makes sense with divided by 32 from bit sets. Degrees, Yeah, but if all those edges are random-ish, then the degrees are very small on average. They are on average 1, I think. I don't see a way here to easily handle something with degree 1 or 2. We split into light and heavy objects if indeed you can easily handle one type, and there are few occurrences of the other type. If there was a node with small degree, then it makes sense to consider its neighbors with brute force. Here, it's not that you want to consider neighbors, you want to keep going. Maybe it makes some sense to consider short edges separately, and to say that for short edges we do something, and for long edges we can just cover them with brute force. We can just keep going. But no, I don't think that technique too is a good idea. The solution is to split the sequence into blocks of fixed size. And I've seen this trick many times, so it's not just for this problem, P7. Split it into blocks of fixed size, most likely square root of n. And for every block, for every position, I want to know if I do a lot of jumps maybe here, where will I exit? Maybe not necessary to immediately the next block. For every position here, I need to know how many jumps I make inside, maybe here 5 jumps. Inside this block. Of course, 5 doesn't exceed size of the block. And where I will go, let's say here we have I equal to 20. So we will go to I equal to 20. I need to know the number of jumps here inside the block and where I will go outside. If I have this information, then I can process a query in square root time. Yeah, exactly. Also, I'm turning off the chat. Now, when we have a query, we will from here see how many jumps we do inside, and we jump out. Then we are at some new position, like here the position 20, this one, and we do the same thing. We'll see how many jumps we do inside the block, and we go outside. The trick is that this thing will have only the time complexity will be equal to the number of blocks to answer a query. So if we start from s, we say while s doesn't exceed n, answer plus equal jumps inside of s, so that how many jumps we make inside the block, and s is equal to where2 of s. And we know that this always moves us outside of the block, and we always move to the right, so it is fast. All right, in square root time we can answer a query, but what about changing something? Well, if I look at an edge going from somewhere, like maybe going from here to there, what can it change in my two arrays, in array jumps and arrays where2? Well, it can affect only this block. So when there is a change of an edge from position, let's say j, then I only need to rebuild block with index j. And I think it's convenient to rebuild this block from right to left, so backwards. Keep going from the right. Let's zoom in on a single block. This is a single block. I maybe changed an edge from here. Now it goes somewhere else. Then those positions don't change actually, you don't need to rebuild it. But those you do need to rebuild. And for each of them, you just need to look where direct edge goes from here. And if from I there is direct edge to j, and if j is still inside the block. So if block of I is equal block of j, then what do? We need to say jumps of I is jumps of j plus 1, and where 2 of I is where 2 of j. J is apparently in the same block, and it will tell you where it will finish and how many times it will jump. Else that's trivial, because jumps of I is just one. You make one jump to get out of this block, and where 2 of I is just the outgoing edge from I, which is j. That's the solution. So when we have an update, we rebuild one block in time complexity equal to size of this block. And because one type of something in the input gives us time complexity equal to size of the block, the other, the number of blocks, time complexity then is best if we choose block size to be square root of n, because then both types will have square root of n time complexity. I forgot to ping people on Discord. We are done with P7. Are there any questions? I said that we can consider this thing as well. Well, we already have rebuilding the structure, but not really this thing. Time of queries. So if few queries change, can I still use what I had before? I don't think we can get the same time complexity this way. We can rely on something like this. If block with S is okay, then maybe do this thing. Else brute force through this block. Maybe something like this is a good idea to try technique number 3, and then if 5 queries were messed up so far, if there were 5 updates so far, then 5 blocks will be bad. So for those, if you ever get to this, you will go with brute force. That seems not very efficient. Yeah. I don't think that's a way to go. We need to stick to technique 1 here. Moving on. We discussed P7. Time for P8. P8, Saria and fun. The update is that there is a sequence, and the update is that one element is shifted cyclically in a range. For example, if we have a sequence 4, 7, 1, 2, 3, 5, 2, 6, and 10. And now we look at this, we have an update about this range, and somebody tells us this thing shifts, then last element moves to the beginning. So we have 4, 7, and now in this range, last element is moved to the beginning, so 6, then the rest is the same. This thing was shifted to the right by 1 because 6 was moved. This element got here. Or in other words, the update isn't about, rotating an interval. It's just about moving an element to some earlier position in the sequence. And we have queries. Count how many numbers equal to k are in some range. The first and the last, only 2 elements change. Yeah, that will be a good idea. But turning out of the chat, because people told me that it's distracting. If we try to split the sequence into blocks, like here maybe this initially, then there are some ways to approach it. First, stupid-ish way is that we see how everything changes. Maybe this is not a good example, but in more general, if we have some sequence and you have split into blocks, and now element from here, let's say 6, is moved somewhere here, then what happens? Everything inside is shifted by 1 to the right. So if there is some element 1 here, there is element 3 here and 2 here, each of them is moved to the next block. So that's one idea, and that's not the most efficient thing we can do. Later we will figure out a way to avoid actually handling those 1, 3, and 2. But we know that once 6 is shifted, then 1 gets to the second block, 3 gets from second to third block, 2 gets from third to fourth block. So indeed we can say that those will be moved. And what can we store for every block? For every block I can have, for example, a map from int to int with frequencies. Frequency. Right? And if I move 1 from first block to the second one, I will decrease its frequency in the first block, and I will increment its frequency in the second block. Instead of map, you can use unordered map, but it will not be much faster. Then when you want to answer a query, you will just have some range, and like in any square decomposition problem, there will be full blocks from which you just grab frequency, and there will be the first and last block affected by the by this range, like intersecting with this range, so then you will go linearly through those. Yes, map adds logarithm to complexity, and map is generally slow. We will want to avoid it. What else can we do here? Instead of a map, like somebody already is talking about in the chat, we can have bigger space complexity. We can have frequency of the number of blocks times the limit for numbers, and we see here that numbers are limited by n. Even if they weren't up to n, we could do coordinate compression, so they would be up to n. We can have this thing, and the number of blocks is, if it's square root of n, then this is n times square root of n space complexity. Let's calculate if that makes any sense. Say that the number of blocks is around, what, 300 by 100,000. That many integers, it's this times 300 divided by 1 million. That's 30 million integers, so that's just 120 megabytes, which is fine. Let's assume that the limits are actually bigger. Let's assume that n is that much, and square root is around 600. So now I'm solving bigger limits than what is given in the problem statement. It should be 4. Now I have 240 million ints times 4, because int is 4 bytes. That's maybe actually short is enough, but let's say we use integers. 240 times 4, that's almost 1 gigabyte. 1 gigabyte is too much, I'm sure. Yeah, 256 is allowed. So if n is up to 400,000, what can I do? Well, we learned in the first lecture that we can choose the block size, and sometimes if, for example, we have logarithm in the time complexity, the block size shouldn't be perfectly square root of n. So here you can adjust some trade-off between time and space complexity. In this case, if I needed space complexity equal to blocks times n, I would want fewer blocks. So I would here try to do maybe 200 blocks. So block size would be bigger because of that. Block size is what? N divided by blocks, so 2000, which is bad, but that doesn't affect space complexity. And if I put here 200, I will have 80 million integers, so 320 megabytes. Still a little too much, but you need to go slightly lower. The idea is that if you choose some constant, maybe it will not be perfectly in the middle or perfectly squared. If there are some things you need to take into consideration, like one part of your solution is slower by logarithm or just has bigger constant factor, or it causes huge space complexity. So the block size might be not equal to squared to decrease the memory usage. All that being said, here it's fine because n is only 100,000, so we can have n squared of n time space complexity. Be aware though that even just taking all that space, it takes time. Allocating big arrays or big vectors, handling anything like that takes time as well. All right. What else can we do here to simplify everything? I don't want to... What I described is already a valid solution. With this array, square root of n by n. Now ignore this because that's not n. We will have 300 by 100,000. When there is an update, we just move last element of every block to the beginning of the next block. We move this element here. In order to move it like that and for every block to know what are the elements there, I would say that we can use a queue for every block. Yeah, a queue should be fine. A queue and frequency map. And then when, of course, we need to rebuild the first and last affected by the update, that's fine, because queue doesn't allow you to access the index. What else can we do? We can avoid moving those elements completely, but this will mess up size of blocks. So let's say I don't want to move this, and just 6 will be inserted to the first block. And because of that, the last block has smaller size, the first block has bigger size, which is temporarily fine if you eventually fix it. So solution number one was, what we already described. Solution number one is split into blocks of size square root of n, sequence I into blocks of size square root of n. For every block, keep q of its in elements and a frequency array. We could do it with frequency map, but it will be much slower. We instead use frequency array because that's fine. The elements are only from 1 to n. Then when there is an update, for an update, move the last element from between blocks. For an update LR, move A of R to block with position L, and move one element per block in between. It was this drawing where I moved 1, 3, 2. That was solution 1. Solution 2 is allow same but only move AR. Block sizes. I want to allow blocks not to be of the same size. For example, if the first block is 2, 3, 4, second is 1, 5, then there is, because already maybe they are not even size, 4, 3, 4, 1, and there is here 5 and 8. And let's say now somebody tells me to move 5 here. How can I do it? I can just erase it from here and insert there. And I will actually insert it in the proper position, exactly where it should be, which is here. 5 gets here. Now we have 2, 3, 5, 4. 5. And yeah, but the sizes will be messed up. So once every square root of n updates, I will rebuild everything. Now, how can I keep every block? It will be just a vector of integers. This is vector of ints. How do I get a of r even? How do you know every number is where? Well, if you have, let's say this is the case. How do I get now sixth element of the sequence? I look at the first block. It has 4 elements. Vector size is 4. So I need to find second element in the remaining sequence. So here, second element exists. I grab it. That's it. That's how you can find a of r. That's how you can find some position. Then when you move an element, you just erase something from one block, insert in some other block. Also, you update the frequency array, right? For every block, you have frequency array. It could be a map, but it's too slow. And we still want every block to be around square root of n size. So we have this fix that in solution 2, once every square root of n updates, we rebuild everything perfectly. This way, it's guaranteed that always block size is at most twice square root of n. Sometimes it can be empty. And that should be. Just be aware that now to get some position, you need to know vector sizes. Or even for every block, you can keep the starting and ending index. The number of blocks and block sizes are still around square root of n. Also, here we solved problem, I think in both solutions. We could solve a slightly harder problem. They can just tell us, remove this element or insert this element here. So insert element x on position I. We can handle such updates, such queries. Time for questions. Oh, and we were forced to solve this problem online because the queries were encoded. So if you think about something like Mohs algorithm, that's not allowed. I don't even know if that's possible, but there must be a reason why they forced it to be online. Maybe so you wouldn't know which element to keep track of. I had one wrong idea. I think it's wrong. I don't see how to make it work. My wrong idea, I think it's a wrong idea, was for every element keep track of its positions. Or actually, if some element appears very many times, so I wanted to split into light and heavy objects, but I couldn't make it work. For every, there are only few elements with frequency greater than square root of n. For those, for every update, I can just modify where they are. But I wasn't sure what to do about elements that don't appear that many times. Yeah. Maybe there is a solution like that. Also, I don't know, maybe there is a solution with polylog time complexity. Okay, then we will move to P9. Also, before that, a short ad for my classes. I'm looking for one person for ICPC coaching group classes. The class size, there are 3 students in the class, including you. There will be 3 students, and the cost is $300 per month. That's for weekly classes lasting 90 minutes. If you're interested, you can write to me in Codeforces, Discord, email. ICPC is a contest. International College Programming Contest for teams. Oh, and your code versus rating should be around 2100 at least. Weekly lessons of 90 minutes. If you are interested in this and you can afford it, then hit me up. Ad over. That. It wasn't an ad if I'm advertising my own stuff. Self-promo. P9. You're given a sequence and something. A functional graph is a graph where for every node we know where it goes. And there is just one outgoing edge. Then this graph always looks like, I think it's sometimes called sunflower, but also, is medus a word in English? I'm not sure. It's always a directed tree where root of this tree is a cycle, maybe of size 1. And it doesn't need to be connected. Possibly this is how the graph looks like. Chat off. This is a possible initial graph, and then we have an update that changes one edge. Maybe this edge is destroyed and instead we have this one or something completely different like here. And we need to answer queries starting from somewhere when we will get to a cycle. Like how many steps it will take for us to actually repeat something. That's the problem statement, and I think that this problem is very difficult. We don't have ranges, so it's not Mohs algorithm. It might be 3, it might be 2. We don't have a sequence, so it's not 1. I would try 2 and 3 during a contest. Maybe it's something about the degrees. Because we have a graph, it might make sense to distinguish into light and heavy nodes based on the input degree. But I don't think that's useful. I don't see a way to handle something with input equal to 1 or input equal to 1000. Can you have multiple cycles? Yes. This thing in particular here is something of size cycle of size 1. It could be actually like here. It could be of this size. Stupid math. Sunflower graph. Nope. I thought that's it. It's a proper name. I don't know that. P7 is a special case. Yes, P7 is similar problem where now everything is directed. So P7 is the same in a DAG, directed acyclic graph, also where order doesn't change. And here we cannot, we cannot split this into some groups where for every group we will rebuild it. So yeah. I will tell you some wrong ideas that I had. I think they are wrong. They didn't seem to work. Wrong ideas. First, choose square root of n random nodes. Always know the answer for those. I hope that maybe if we keep moving from some query, then we will always get to one of those important nodes. That's not true. And also I don't know how to keep the answer for this. Then second is maybe maintain the graph, trees and cycles. Actually, this is possible, or something like this is possible, but I will not discuss it. This problem can be solved with link-cut, but I don't know the details. Radeusz told me it's possible, and he also told me how to do it, but I don't want to understand it now. So it can be solved with link-cut. We don't care. We want to do it in square root time complexity. Jero, I will read your comment in a moment. What else I thought about? When we change an edge, so an edge from I, look backwards at nodes before I. Nodes that were from which you can get to I. I thought that maybe for them we will rebuild something. Another idea, for every node, know where you are after square root of n steps in order to make such big steps. It's a bit similar to a baby step, giant step. Nothing in this list worked for me. Yeah. What is a correct idea, but still it's hard to execute. Maybe I will read what Jero said. Square decomposition by time, yes. Yes, that's a correct solution. Indeed, we start by saying square root decomposition by time, and we will rebuild graph question mark after square root of n queries. That's something we will try. But now, given the initial graph, like this one, if now something small changes, like red edge got destroyed and the green one appears, we need to be able to answer a query. And when I thought about it, I just couldn't do it. And the issue is that we need to combine it with the second idea that we need to do it offline. Offline meaning you can read the input and then do something about it, which is very surprising. I think that the fact that we need to do something offline here makes the problem much harder. At least it was the case for me. For a long time, I couldn't come up with the fact that it's offline. Because all those ideas I did have, but without this fact, this idea is useless, I believe. How is it useful that it's offline? Well, two things. First is we can look at many queries at the same time, many updates. And second is we can look at the future. For example, we also know what queries there will be, from which node you will start. That's not really useful. It's useful that we know what will be changes in this block of square root of n queries and updates. Here's what we'll do. Let's ignore the fact that this is green. I look at changes that will happen in the block of square root of n queries. Maybe this will change, maybe this will change, maybe this will change. I'm looking at those. And now, this I claim splits the graph into square root of n parts. I can remove the edges that here will not necessarily exist, and I can leave just the remaining graph, which is like this, like that, done, I think. Again, I got sunflower graph. I got a graph where every connected component is a directed tree. Maybe the root is a cycle. Oh, I had those, right? So I keep forgetting about those. Let's also make them in white. Like this. All right, we have a graph. And now we know that, what do we know? we start with the set of those erased edges. So always when there is a query, we have some temporary edges. First we have this thing, this one, and I liked this thing. Oh, this was a single node, right? Because this is cut. And the last in yellow, this thing. Those yellows, they are temporary, just for the first query. Then there will be an update and one of them will be destroyed. So then for a moment I remove all of them. They were temporary, I know that. And I now say, oh, there is this edge, there is this edge, and there is this edge. So the white graph on the right is, it stays. I need to do some preprocessing there, and then there are yellow temporary edges. All right, now what is the solution? For a query, always, if I start from here, I know that I will move to the root of this tree. We see here the, maybe let's again remove the yellow. I will at least move here. This is the start. Start. I will get at least here. And now there will be a yellow edge. And I know what edge exists right now. Let's say it currently goes here. So I traverse this edge. Now I am here. And I again go to the root. In this case, the root of the tree is this cycle of size 3. So I know, well, I will here keep going forever. If I know size of this cycle, then I know the answer. Of course, as I went, from here in constant time I jumped there, then in one jumped here, and some number of jumps here. Always, every connected component, every white connected component is a tree, and you need to know what is your depth, length, the distance to the root, and whether root is a cycle. If root is a cycle, then what is size of this cycle? Or maybe there is a yellow edge going out of here somewhere, and depending on the query, it can be different. It seems that the code answering query is the current node is initially starting node, then while true, also answer starts as 0. Answer plus equal depth of the current node in its tree. Node becomes root of this node in this tree. If is cycle, we need to figure out a way for that. Answer plus equal cycle size and return. We know the answer now. Return answer. Maybe. Let's say this is a function. Else, we don't need else because I used to return. Else follow yellow edge. Yellow is temporary, something that will in a moment completely change. There are at most square root of n yellow edges, because yellow is just, we are looking at square root of n, a block of square root of n queries and updates. Everything that is not modified there is white, and this is most of the graph. We will have square root of n connected components, and there are always some yellow edges between them. So this is how we answer query. With one difficult part, which is easy to miss, I think. Something like this can happen. There is a tree. Let's say that this is the start. And now you got to the root quickly in just one operation, but of course you added here depth of the node, so you added what, 3 to the answer. Great. Oh, and if we follow yellow edge, then that's also +1, answer ++, because we make a step. Okay, but there is a yellow edge from here. Let's say that it goes somewhere here. And there is also maybe a yellow edge from here. And now an issue is here, maybe like that. So they are directed trees, and there, from every root there is an edge to somewhere, usually some other tree, but actually it can also be to the same tree. But even if not to the same tree, later we can go back to the same tree. And now, what is the answer where we will stop? Not necessarily in part of the cycle, actually, but part of the cycle, but cycle is also created by yellow edges. If we now are here, we should stop at the red node, because this is part of already existing path. This is how we went from start. From start, we traversed here, then we traversed this thing, then we traversed here. Oh, that's repeated something. The yellow edges created a cycle. I will now mark a cycle in red. This is a cycle. It isn't obvious, it isn't root of the tree. So what we need is, for this yellow node, I will call it node V. For V, which is where we got directly from some other root, we need LCA of start and V. And that will be the answer. We need also depth of that to know how many steps we make from V to the end. Which means that here, at the position of question marks, I should also check if I'm currently in the same tree as the starting node, and if so, I need to find LCA between them. Or I need to know visited components or visited roots, something like that. Something needs to be done here. Now, one way is to literally treat it as LCA, and then when rebuilding the structure, so when building the y-directed trees here, we can do some pre-processing for them. So we could answer LCA. We could do n-log-n's pre-processing, or with the RMQ, fast RMQ queries in constant time, or we can do it in linear time to then ask maybe a segment tree in logarithmic time about LCA. There are many possibilities, but we will get logarithm there. And when we have square root solution where one part of the solution has logarithm, then we will choose our square root of n not exactly to be square root of n, and I guess that we'll have time complexity of n square root of n times log of n. I assume that n is equal to q. We indeed find LCA only once per query, and it would be nice to do it in square root of n. But still doesn't mean that I can do it linearly, because size of the tree, depth of a tree is linear. So how can I improve it? I believe that it's easiest to just split, be prepared for this and split everything more. When we are looking at white graph with yellow unnecessary edges, so those removed by yellow and those new yellow, we can split white connected components a little bit more to avoid this issue. Square root of n jump pointers, but pre-computing them is, oh, I see. That's a good idea. Okay, so we can find LCA by pre-computing square root of n jump pointers. Makes sense. Makes sense. So that's linear precomputation and logarithmic answering queries. So you're right, and then it's clear n squared of n, but I want to just describe something without LCA. Okay, so here's one thing that we can do. When looking at a wide subtree, mark as interesting, looking at the directed tree, mark as interesting all nodes such that we will start a query there, or there is a yellow edge coming in. Maybe here, here, and this one. Again, mark as interesting all the nodes such that we start there, or there is a yellow edge coming in. And now, also mark as interesting all the LCAs of those. So also this node gets marked. In other words, every node where at least two subtrees contain an interesting node, which can be done in linear time. This is just DFS for a tree where subtree returns false or true whether it has at least one interesting node. And here comes a trick. Also split at those nodes. We got square root of n interesting nodes at most in total, and we should split in them as well. So I cut here, 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 and here. Now the answer must be the root. I didn't like the fact that I'm looking for LCA. I wanted the answer to always be the root. But the answer can only be an interesting node or like LCA of interesting nodes. And if there are k interesting nodes, then there are O of k possible LCAs. I don't need to find any jump pointers or anything like that if I just cut there. I will still have square root of n connected components, the trees, so still the time complexity is fine, but I just have slightly more of them, maybe 2 times square root of n. So there were multiple ways to avoid LCA. Ways to avoid LCA. Step 1, well, don't avoid, just make it fast. For example, Jero described how to do it with jump pointers of size square root of n, which can be precomputed in linear time. Then you can answer a query in square root time. Then second way is to cut add interesting nodes in advance. This creates more components, connected components. Similarly, cut so that every connected component is of size square root of n. That's what I came up with. This is what Radeusz told me is possible as well. I wanted to do, because I wanted to find LCA in linear time. This avoids LCA. This makes it fast. I will now find LCA just by brute force. I will keep moving the deeper node up to a part. So this means as the pre-processing before a chunk of square root of n queries and updates, when we find those connected components, the trees, I don't want any tree to be big. If it's big, I want to cut it more, which can be done easily with DFS. If you see subtree with size at least square root of n, cut it. We actually don't care about sizes. I just want to guarantee that no tree, no connected component has height longer than square root of n. Because then LCA can be found in linear time. LCA with brute force is just O of height of the tree. I don't know, maybe there are other ways too. All of those actually avoid logarithm, and in any case we have n square root of n. As always, I assume that n is equal to q, because I don't want to compute exactly whether I'm putting here q or n. But I'm splitting queries into chunks of size square root of q, I guess. So I don't think it, maybe it will be square root of n plus q. Maybe it here also will be n plus q. For sure, we don't exceed this. And we don't use any sets, maps, so everything is fast. Any questions, chat? How is the stream with this turning the chat off and on? Is it fine? It would be best for me if it was automatic, but I don't think that can be done. Like automatic how? We covered P6 through P9. Again, thanks to Christmas, because actually many problems, including this one, I just took from him, from his list that he covered with students a few years ago. One more nice thing is, I recommend the link from this comment by Box. This plug, it's a blog with many problems, mainly about Mohs algorithm in non-trivial examples. Well, I don't think that this blog is perfect. There were some places where I didn't understand something. But it's a good collection of problems, at least. And it seems that many of them are related to harder versions of Mohs algorithm. At least what I've read. So check out Box's comment, the plug. I will also put it in the blog. So I think we're done. One last minute for questions. I want to thank everybody for putting so many links and useful problems and useful links in the comments here. Though it's now overwhelming. I didn't check out all of them. It would take too much time. But it's great that once there is a blog like this one, now there is a source of tens of problems. Yeah. If I had more time and will, I would maybe make this into a dream contest. That would require preparing those problems, but I think that dream contests should be better than this. They should actually create new problems, like in Matrix Expo dream, where there should be new problems that just extract some technique and won't force you to use it, and nothing more. Which here isn't that bad. Alright, thank you everybody for watching. See you again in a few days. I will get back to problems of the week, maybe more like problems of the month now. Maybe this Sunday, maybe not. We'll see. If not this Sunday, then just after that, like Monday or Tuesday, there will be the next stream. Bye everybody.